Hello. Hello.
So good morning, sir.
Good morning. Good morning, Sujant.
Sir, can you share the class notes from starting? Like I have joined the course later, so
Okay, no problem. Day-wise notes we have, okay? That is in the group itself. So I will share it one more time as a message, okay?
yes,
Because
yes,
otherwise the file size will keep on elongating. So that's why you can see that first day, second day notes like that, okay?
yes, sir. Yes, sir.
Right, I will share it after the class once. Okay, just let's wait for a minute and then we will continue. Hi, Lokesh.
Good morning.
Good morning. Still Charan and Manali there. Okay, let's start now. Okay, last class we discussed about what is the electric potential energy, है ना? And last thing we discussed was the electric potential. Okay, right? Electric potential energy and electric potential. What is the difference between these two? The difference between these two is what electric potential energy when we are discussing. That means it is between the pair of charge particles. Okay, between any two pair of charge particle we are discussing. Okay, but when we are writing electric potential, then it is what potential energy per unit of charge particle, है ना? So that is the difference between potential and the potential energy. Is that clear? So whenever we have to write the electric potential, okay, when we have to write the electric potential, then what is the thing needed to write about electric potential? What are the things needed? We need to know what is the charge particle and whether the charge particle is a positive one or negative one, and where we want to calculate the potential due to the charge particle. Okay, so that gives us what electric potential at a point. Okay, now not every time we will have to calculate the potential due to a single charge particle. Okay, sometime we have to calculate electric potential. Okay, electric potential due to combination or due to multiple charges. Okay, due to what? The multiple charges. Multiple point charges are there in a surrounding, and we want to calculate potential due to these multiple charges. What we should do it in that case? Let's say we have many charges here, Q1, Q2, Q3, Q4, like that. Okay, and we want to calculate potential at the center. So what we will need? We will need what is R1, we will need what is R2, you know. These R1, R2, R3, R4, these are representing what? These are representing the position of charged particle with respect to what? Origin. Okay. So if we want to calculate potential, right? If we want to calculate net electric potential, net electric potential at the center. Okay, net electric potential at center or origin. What we should do it? Tell me. To do that, should I do one thing? Let's calculate what is the potential due to charge 1, second charge. So if we calculate potential due to all these charges, right, and add them, and one more thing we learn that potential is a what kind of quantity? Potential is a scalar quantity. What we have done, learn that potential is what? Potential is a scalar quantity. So if potential is a scalar quantity, that means what? If I want to find the net potential at any point, it will be just the sum of individual potential. Understood? Not the vector sum. It's just a sum. Okay, so that's why net potential at any point, what it will be? V1. Potential due to charge 1, how much it will come? K Q1 by R1. Due to second charge, K Q2 by R2. Third charge, K Q3 by R3. So like that we can add all these potentials, है ना? And then what will happen? We will get the net potential at the origin. Understood? So at any point, if you want to calculate the net potential, then what you should do? You can calculate potential due to all the charges, and then you can just add it. Just what? Just add those potential at that point, and that will give you the total potential or net potential. So potential is positive and negative, but potential is not a vector quantity. Potential does not have any direction. Is that clear? Please tell me what we discussed till now. Is that clear?
Yes, sir.
Yes, sir.
Right. Let's take an example, okay, and try to understand what we have just done. See, in this example, what I'm going to take, an equilateral triangle is given to us, okay? An equilateral triangle is given to us. Side of equilateral triangle is, let's say, something A, okay? Side of equilateral triangle is A, and at the three vertex, 3 plus Q charge is kept. All the three corners have what? The equal charge. This is plus Q, this is plus Q, and this is what also? Plus Q. Okay. Now I am asking, this is the centroid. Okay. My question is find net potential at centroid. Find net potential at, okay, which point we have to calculate the net potential? At the centroid. Okay. Find net potential at centroid. Okay, that is the one thing. Acha, tell me one more thing. What is net field at centroid? What is the net field will come at centroid? Is it going to be zero? Please tell me. We have calculated this question. When we discuss about electric field concept, we calculated what is the net field, right? Remember? Please tell me. So what is the net field will come at center? So net field answer will be how much? 0. Understood? Why net field is 0? Because 120 degree, 120 degree, 120 degree, na? All three vectors will be at 120 degree, na? So in this question, can we say net field is 0? And what will be net potential? So net potential will be, tell me, centroid to vertex distance. What is that? A by root 3, na? Distance from centroid to the vertex in equilateral triangle. How much is that distance? That distance is A by root 3. So can we write it K Q divided by A by root 3, and like that, how many charges are creating the potential at that point? 3 charge particles. So what we are getting, KQ by A root 3 into 3. So we are getting 3 root 3 KQ by A. Understand? So this is the net potential at which point? At the centroid due to these 3 charges. Is that clear? Please tell me.
Yes, sir.
Please tell. Clear this question? Let's see the next example. In this example, what is given to us? This is the x-axis. Okay, and this is what? X-axis given to us, and this is the origin. I'm going to keep equal charges at a different point. Here I kept a q charge. Here I kept another q charge. Here I kept another q charge. These distance are what? This distance is a, okay? Or let's take it, this is 1 meter. This is 2 meter. Third charge is kept at 4 meter. Fourth charge, where it is kept? Can you tell me? 8 meter. From that point, okay? And like that, there are charges up to where? Up to infinity, that pattern extended. Okay, this pattern is extended up to infinity. So they are asking in the question, find net potential at origin. Okay, or let's say not here what I have taken. So let's see that how much we are going to get it. Please tell me what we will do it here. So we have to calculate, if I want to calculate the net potential at origin, do I have to calculate potential due to each of the charges? So for first charge, how much it will come? KQ by 1. For second charge, how much it will come? KQ by 2. For third charge, how much it will come? KQ by 4. Fourth charge, KQ by 8. Like that. Please check it. Do you find any pattern here? KQ common 1 plus 1 by 2. Right? Check it.
GP form.
Is it an AP or is it an GP?
G.
Right. So this is what? An infinite ZP. And what is the common ratio of that infinite ZP? Right or not? That goes up to infinity. So common ratio of this infinite GP is 1 by 2. So what is the sum of an infinite GP? So sum of an infinite GP is A by 1 minus R. है ना? Sum of an infinite GP is A by 1 minus R. So A is 1 minus. What is the common ratio? 1 by 2. So what we have? KQ1. 1 minus 1 by 2. So 1 by 2 it will become. What is our answer? 2K into Q. Please tell me, clear up to this? So here,
Yes.
what we are doing, whenever we have the multiple charges, what we are doing, our approach is to calculate the potential due to each of the charges. Okay. and then just add it like a number. Okay, now why? Because potential is a scalar quantity, so it will not have any direction. So net potential at any point is going to be what? It's a sum of all the potential created by other charges in the surrounding which is present. Understood? So these were the potential calculation due to what kind of charges? Due to point charge. Now let's calculate potential due to what? Some distribution of charge. Understood? Let's calculate potential due to what? Some distribution of charge. Distribution means charge, means linear charge distribution. Okay. What is the potential will come that we are going to calculate it. Is that clear? Please tell me. So let's calculate the potential due to what? The distribution of charge. Okay. Electric potential due to distributed charge. Okay. So due to distributed charge means what? Let's say due to the ring. Uniformly charged what? Ring. Okay. Uniformly charged ring is given to us. Let's calculate the electric potential due to a uniformly charged ring, how much it will come. So what are the 2 points where we are going to calculate it? First point is going to be at the center of the ring. Okay. So tell me, what is the electric potential at the center of the ring? Please tell what will be electric potential at the center of ring? This is a uniform charge distribution.
Q by R.
KQ by R only will come, isn't it? Because it's a potential calculation, not the field calculation. Be careful about the question. Did they ask the potential or did they ask the field? Okay. So let's say here, what I have given, total Q charge is given to the ring, and the radius of ring is how much? It is R. So what is the net potential at the center will come? So net potential at the center will come KQ by R. Right now, matlab it's like every small element will create the same potential, है ना? And then what we will do it? We will add all these potentials. That gives us what? The total potential at the center. Understood? Now, the second point we have is on the axis, isn't it? These are the two important points where we have to calculate the everything. Means in the field calculation also we have done the same thing. We calculated field at the sensor, we calculated field on the axis. Now same thing, we are going to calculate potential at the center, and then we will calculate potential on the axis also. Okay. So let's see and let's calculate it. What is going to be the electric potential on the axis of a ring? Okay. So let's say a ring is there. Ring has a charge distribution like this. Okay, linear charge distribution will be there. Na? A ring is there which has uniform linear charge distribution. Linear charge distribution means what? Lambda. Charge per unit length will be given in the question. Okay. So a linear charge distribution is given to us. Okay, something like this. And the radius of ray is R. Again, total charge on the ring is Q and radius is R. So can you tell me what will be lambda? Lambda will be Q by 2 pi R. And lambda is the linear charge density. So what will be linear charge density? It's going to be charge per unit length. Charge per unit length means Q by 2 pi R, we can write it. Now let's say I want to calculate at this particular point. This point is what distance? This point is something x distance from the, okay, this point is what? Something x distance from the center of the ring. Okay. So what I will do it first? Will I calculate, let's say there is a small element, okay? small element having dq charge. So first what I will do it, I will calculate due to a small element having charge dq, what is the potential at this point P? The small potential at point P, how much it will come? Will it come K, small amount of charge dq, divided by, can you tell me what is this distance? R square plus x square we have, isn't it? So K dq by distance, isn't it? That is how we calculate the potential at a point. And we have divided this ring into many small element. A small element, I can consider it as what? A point charge. Okay. So we got the small potential at point P. If I want the net potential at point P, what we should do it? We should integrate that, isn't it? If I integrate it, K dq by under root of r square plus x square. Why we did not discuss anything about the component or anything? Because we are calculating the what? We are calculating the potential, which is a scalar quantity. So that's why we should not worry about the direction here. Okay, we can directly go for the integration. How much it will come? K. Next thing you see that r square plus x square is outside, and dq integration, is it just a q? dq means all small amount of charge. If I add it together, what I will get it? After adding them together, we are going to get it as the total charge. So that's why net potential on the axis of a, see that, net potential on the axis of a ring is how much? Kq by under root of r square plus x square. Electric potential, it will be at x equal to 0. That means center. And as we go away from the center, what happens? Potential will keep on decreasing. And after infinite distance away from the ring center, or very far away from the ring center, what will happen? The potential will become 0. Understood this one? Please tell me.
Yes, sir.
So this is the electric potential due to uniformly charged string. Now you see this potential. Acha, potential and potential energy relation is known to you. Please tell me.
Yes, sir.
Potential is what? Potential is potential energy per unit charge, है ना? So अब if potential energy between the two charge particle is given, then we can calculate the potential, isn't it? Or what else? If I know potential of a certain point, right? Let's say in this space, I know the potential of a point. Can I multiply the charge present there? And that will create what? The potential energy of the charge particle. Understood? So if we know what is the potential at this point, okay, if we know what is the potential at a particular point in this space, right? Then if I multiply the charge present there, that makes it what? That makes it the potential energy of that point. Potential energy of that charge particle present at that point. Is that clear? Please tell me, clear up to this? What
Yes,
we
sir.
have discussed? All of you,
Yes,
please
sir.
tell me. Right. Okay. So let's see the next part now. Let's take an example here. Okay. Just based on what I discussed with you. Okay. See, in this example, what is given to us? A ring is given. Okay. A ring is given to us. Ring has a distributed mass plus q, and ring radius is given as r. Okay. There is a negative charge particle here. Its charge is minus q and mass is m. And this negative particle is where right now? Uh, root 8r distance from the axis. Understood? This negative charge particle is right now where? Root 8r distance from the axis. Okay? Now what is going to be done? This charge particle is going to be released. So what will happen? Will it move along the axis towards the center of the ring? Please tell me. If I leave this charge particle at this particular point, let's say this point P, then what will happen? This charge particle will be attracted towards the ring, right? Attracted towards ring. So it will reach the ring with some velocity, isn't it? The question asks, find the velocity of ring. Okay. The question asks, find the velocity of ring. Okay. When, sorry. Find the velocity of the particle, not the ring. Okay. Now, find the velocity of this charge particle. Okay. Find the velocity of charge particle when it reaches the center of ring. Understood? It is released from which point? That is given to you in the question. And they are asking the question, what will be the velocity of this charge particle when this charge particle is going to reach the center of the ring? Understood? Please tell me. Can you tell me what we are going to apply in this question now? Please tell me, what are we going to apply in this question?
Mechanical energy conservation.
Yes, work energy theorem or energy conservation. Both are going to give us the same answer. Okay. So, but when you can apply the work energy theorem also, or you can apply the energy conservation. It is always better to apply energy conservation when we know the expression of potential energy clearly. And when we know how to calculate work done clearly, in that case, we should apply what? The work energy theorem. Okay, both are same thing. It's not different than each other, but depending on which equation is more convenient in application, that we should apply. Okay, so here it will be better if I apply the energy conservation. Okay, so please tell me, if I am going to apply the energy conservation, what is the equation I am going to get it? Check it now. What equation I am going to get? See, can you tell me, if I am going to apply energy conservation, K initial plus U initial equal to K final plus U final? Initial means what? Is the point P is the initial point, and when it reaches the center, that is where I want to know everything. So that is my final point. So tell me, K initial, what is K initial? 0. Initially, the charge particle is released in this question, isn't it? Initially, the charge particle is released in the question. So initial kinetic energy 0. What is initial potential energy? अब these two are not the point charges. Na? So you cannot write it K Q1 Q2 by R. Can you write it K Q1 Q2 by R now? Can you write it K Q1 Q2 by R for the ring and particle? No. But yes, but can we still write it? What is potential due to ring at this point P multiplied by the charge present at point P? Right now, potential multiplied by the charge present there, that also gives us what? The potential energy. Understood? Potential multiplied by the charge present at that point gives us the potential energy. So what is the potential at that point? Is the potential at that point is kq by under root of r square plus root 8 r square. Please check it. R square plus. This is the potential at the initial point. Na? And what charge is present there? The minus q is present there. So this is what we have the u initial for us. Now what is k final? So when it reaches the center, it will have some kinetic energy plus it will have potential energy. What is the potential energy now? So I have to write potential at the center of ring, isn't it? What is the potential at the center of ring? KQ by capital R. And what is the charge present there? So same minus Q, na? Same minus Q. Earlier it was at P, and after the movement, it reached which point? It reached the center of the ring. Understood? So K initial plus U initial equal to K final plus U final. We got it. Understood? So now we will simplify it. Check it what we are getting. Are we getting K capital Q minus Q? And look at that, root 8R why it was given, so that calculation will be easy. So 8 plus 1, this is coming 3R. Send the other one this side, K capital Q, है ना? Minus Q is there. So if you send it other side, this minus Q will become plus Q, na? Just check it. है ना? Check the calculation once. That will become plus K capital Q small q by R, and that is equal to half m v square. So half mv square, what we have? K capital Q small q R common, 1 minus 1 by 3. That is what? 2 by 3 we have. So what will be the velocity of charge particle when it reaches there? The velocity of the charge particle is coming 2 into 2, 4 K capital Q small q by 3 Rm under root. Please tell, understood this question? So here what we did, we again used the energy conservation only. But what is the difference here in this question and the earlier question? So earlier question we had the point charges with us, है ना? All the particle involved in the motion, all the particle involved in the question was the particle point charges. So that's why we could have directly used K Q1 Q2 by R to calculate the potential energy. But in this question, what happened? One is a body, one is a particle. So here I cannot apply K Q1 Q2 by R directly. So what we did, we first try to find out what is the potential of a charge ring. And in that potential, if a charge particle enters, then it will start having the potential energy. Understood? So this is what we have done it in the question. Clear?
So, like how to solve this question with the work energy theorem? Like force, like a work is equal to force into the displacement. So force can be
Mhm.
written QE into X.
Force, you can write it.
Charge into electric field.
Yeah, but electric field will be variable here.
Like we have formula, it's KQX by rho R square plus X rho
KQ by R square plus X square to the power
Q by 2.
KQ by R square plus X square to the power 3 by 2. The force will become what? Q into E. The small amount of work done will what? KQX by R square plus X squared, R square plus X squared to the power 3 by 2. Then we will write it dx. Okay. Then we will integrate it. Now check it now.
Yes, yes.
So KQ x by, you will see same result will come in KQX. It will be R square plus X squared to the power 3 by 2. What is the charge here? Charge is Q here. Force into a small displacement, that is a small work done. Let's integrate it. Okay. So here integration, what you have to do it? You have to consider R square plus X square as something Z. 2x dx will become dz. Then you integrate it, then again bring it back in the x format, and then put the limit. You will get the same expression what you have written here and this one. Okay. The same expression will come only with more and more calculation. Understood? Please tell me.
Yes.
So that's why I said that if it is possible to write potential energy in the energy conservation equation, prefer that one. It's not like that work energy theorem is not going to give the answer. Yes, it will give, but with lot of calculation. Understood? That's why we are preferring what? The energy conservation in the process. Okay?
Yes, sir.
Because you see, the energy conservation is just a special case of work energy theorem only. So we have calculated potential due to what? A ring, है ना? Uniformly charged ring at the center and on the axis. Next is what? Electric potential due to circular arc. Okay, electric potential due to what? Circular arc. But if it is a circular arc, we are calculating where? At the center of the circular arc only. Okay, not every point, only where we are calculating at the center of a circular arc we are going to calculate. So if I say this is a circular arc and this is the center at which we want to calculate the potential, let's say arc has what radius? R radius, and that has uniform charge distribution, and it is arc now. Will it be better if I give you linear charge density lambda? Na? Lambda is what? Lambda is the linear charge density or charge per unit length of the arc. Okay, so lambda is the linear charge density we have, and we want to calculate the potential at the center. So tell me what will come. Again, what we will do it, and this arc must be making some angle, na? Arc must be making some angle theta. Please tell me how much it will come. See, any arc you consider, this arc is there. On this arc, you consider any element, any small element. It will have some dq charge. But look at that, is the every element, every small element of the arc is exactly r distance away. So if you calculate a small potential at the center, how much it will come? K dq by r, we will write it. So net potential at the center, if I want to calculate it, can we say that it will become K dq? Can I write it K and integrate it? The K and capital R is constant here in this question. So integration of dq will come. Integration of dq means what? Kq by R will come. What is the Q here? Can you tell me what is the Q here? Q is the total charge on the arc. Q is what? Lambda is the linear charge density. Okay. And what is the Q? Q is clear about this one. What is the Q here? Lambda into R theta. Lambda is the linear charge density. है ना? Lambda is what? Lambda is the linear charge density. And if this arc is making some angle theta at the center, so length will become how much? R into theta. Lambda into R into theta. So what is this Q here? Q is here the total charge on the arc. Understood? So you can also write this formula. Q, you can write it lambda r theta divided by r. You see that if you simplify it, r and r gets cancelled out. K lambda theta we will have. So no need to remember the multiple formula. Okay, just try to understand it. That if I'm going to calculate due to a circular arc, then what I'm going to get it? I will just get it K lambda, sorry, KQ by R. Because why? Because in case of arc, every point on the, every the center will be exactly same distance from the center. Understood? Now, next one, let's calculate. Let's take an example here. Due to straight wire, infinite wire. Okay. Next, the third one we are going to calculate it. Electric potential for the ring part is clear. For the complete ring we have calculated. Then we have calculated for the arc. You know? Next, electric potential due to line charge. Okay, line charge you can call it, or you can call it thin wire, you can call it. है ना? Electric potential due to line charge or thin wire we are going to calculate it. Okay, so please tell me what will happen. Electric potential due to line charge or thin wire we are going to calculate it. So two cases we are going to discuss. First case, it is going to be, the point is going to be along the line itself, collinear point. Okay, first we are going to discuss about what? Collinear, or you can say that coaxial point. Meaning is what? See, something like this. Let's say a wire is given to us like this. Okay, length of the wire is something L, and it has a uniform charge distribution like this. Okay, length of the wire is L, and the charge distribution is something uniformly given to us, and the uniform charge distribution lambda is given. Okay, so here I am going to take the point where I want to calculate potential due to wire at this point. Understood? Please check it. Do you understand the point? Is the point is along the wire itself? If this is the wire orientation, the point is here. Means the point is lying along the wire itself, not perpendicular to the wire. Second case, we will calculate it for the point which is perpendicular to the wire. Okay. Now, tell me, we want to calculate the potential due to this one. I am going to calculate somewhere here. Okay. I am measuring that distance from the end of the rod. This is the point P where we want to calculate the potential. Tell me, how do we calculate it then? So, what is the first step I will have in the potential calculation? So, I want to calculate at point P. So, what I did, I am going to consider a small element. Okay, small element, linear element of what thickness? Of dx thickness. Can you tell me what will be the dq charge on that small thickness? So dq charge on the small thickness is going to be how much? It is going to be lambda into dx. Lambda is the linear charge density. So lambda into dx will give me what? The charge on the small element. Okay. Once we got the dq, what next we should do it? We should calculate potential due to this small element. I've looked at that small potential. If I want to write it at the point P, then what I will do it? I will calculate the potential due to this small element at point P. So how much it will come? K dq. And where is the point P from this element? Is the point P is x distance from the element? Please tell me, is the point P is x distance from the element? So this element will create how much potential at that point? K dq by x it will create. Understood? So, and you just check it, it's just a scalar quantity. So net potential at point P, if I want to calculate it, should be integrate the k dq by x. Now check it. K, what is the dq we have? dq we have lambda dx divided by x. What will be limit of x? Can you tell me? So rod is starting here and rod is ending here. Is the limit of x will be a to a plus l. Please check it. Please check it. Please check once. Can I say here the limit of x is going to be a from a to a plus l, because our x will start from one end of the rod and it will finish it at the other end of the rod. So what will be limit? Lower limit of x will be a and upper limit of x will be what? A plus l. Okay. Now let's simplify it. K constant, lambda constant, dx by x integration, how much it will come? Ln x na? Dx by x integration, how much it will come? Ln x will come. Lower limit and upper limit is known to us. So what we have? K lambda. Is it coming ln a plus l minus ln a? Can I write it just this one? Please check it. Ln a minus ln b. Ln a by b na? So please tell me, do you understand what is the potential at point P? Net potential at point P if the point P is lying along the wire. Tell me, where did we calculate the potential? The first case we are calculating, point is lying where? Point is lying along the wire. Understood the first case? Please tell me. Is the first case is clear? Net potential at point P, how much we got it? K lambda ln A plus L by A. Clear up to this? Please tell me. All
Yes,
of you, please tell me, are you clear to this?
yes, sir.
Yes, sir.
Right. Where will be the second case? On the perpendicular bisector. So in this question, little bit difficult integration will come. So I will explain you about that one. Okay. See, what will be approach? Tell me. Can I say there is a linearly charged rod? Linearly charged rod is there. Lambda is the linear charge density of the rod. Okay. Next is here I am going to consider the length of rod is what? Something L. Okay. And we want to calculate the potential at a point. This is the point P, and this distance is given as perpendicular distance. Let's take the perpendicular distance as something A. Understand what is the perpendicular distance? The perpendicular distance is what? A given to us in the question. Right? The point is not along the wire now. The point is what? Perpendicular to the wire. Now if I want to calculate the potential at this point, what I should do it? Can I take at a distance x again? Can I take a small element, and the small element will be having what length? Dx length. You see that? Are we following the similar process for whatever we have done it in the field calculation? Whatever we did in the field calculation, exactly same approach we are following. Even in the field calculation, what we used to do? At a distance, we used to take first a small element. We calculate field due to a small element, right? But we were not directly integrating the field, a small field. Why? Because field was a vector quantity. So that's why we could not integrate it directly. But here, potential is a scalar quantity. So what happens here, once we got the small amount of potential, we can directly integrate it. Okay. So let's first tell me what is the potential due to this small element at this point. Tell me, what will be potential due to this small element at this point? What will be dq? First of all, tell me, is the dq is again going to be lambda into dx? And small potential at point P, if I want to calculate, if I want to calculate the small potential at point P, so it will come k dq divided by distance of element to the point, na? Because elements are point charges only. Rod is a distribution of charge, but if I consider a small part of rod, then it will act like a point charge. Can you tell me what is this distance? Is that distance is under root of x square plus a square? Under root of x square plus a square. The small potential at this point, will it come k dq under root of x square plus a square? Please tell clear. So if I want to calculate net potential at point P, dq by under root of x square plus a square. Now just check it. What we have here, k. What is dq? dq is lambda dx divided by under root of x square plus a square. That integration we have to do it, okay? And what will be limit of integration here? Please tell me. So if you go one side of this center of rod, then you are taking plus L by 2, and if you are going other side of the rod, then what you are taking? You are taking minus L by 2. So that means here the limit of integration will be what? Minus L by 2 to plus L by 2. Is that clear? What is the limit of integration? Minus L by 2 to plus L by 2. So what will come outside? Check it. K will outside, lambda will outside, and this is integration of dx by under root of a square plus a square. The limit of integration will be minus L by 2 to plus L by 2. That is the net potential. Can you do this integration? Please tell me. Dx by under root of x square plus a square. Can you do this integration? You have to do the substitution twice. Remember this integration? Anyone remember this integration? We have to do the substitution twice in this question. Please tell me. Clear? So please do this integration once, okay? Everyone clear? What we discussed till now, please tell me.
Yes, sir.
Right? So this integration, you finish it, okay? And today I will try to send it you some questions, okay, to do it. Okay, please tell me, all of you, what we discussed till now, understood?
Yes, sir.
Yes, sir.
Right. And all the notes are available in the group, okay? I will just send it because you have joined it late, so that message won't be visible to you. So I will just resend it once, okay? Then you can just go through those notes, okay? Right?
Okay.
Yes, sir.
Surely. So clear, everyone? What we discussed up to potential and potential calculation.
Yes, sir.
Surely. So let's meet it tomorrow then, and then we will go back to the mechanics part and continue there.
Thank you, sir.
Right. Thank you so much, everyone. Take care.